We are going to be exploring describing data with numerical measures. Specifically, in this one, we're going to be exploring measures of central tendency. So we're going to be learning how to calculate measures of location. The purpose of measures of location is to pinpoint the center of the data, and these results are often referred to as averages. For example, the average U.S. home changes ownership every 11.8 years, and the average American home has more TV sets than people. There are 2.73 TV sets and 2.55 people in a typical home. And so that's kind of what we're looking at is measures of central tendency or measures of location in this lesson. So, in this lesson, we're going to be learning how to compute and interpret the mean, median, and mode. We're also going to learn how to compute a weighted mean and compute and interpret the geometric mean and understand what the geometric mean really is. So, measures of location. There are three measures of location that we really look at, which I also refer to as measures of central tendency. Um, so, these are mean, median, and mode. There's different symbols to use when working with the population and when working with a sample. So, note what I said. Population versus sample, there's different symbols that we use, and we're about to look at those in just a minute. The arithmetic mean is the most widely reported measure of location, so often when we say, calculate the mean, what we're really looking at is the arithmetic mean. And so, yeah. So first, looking at population, this is the formula for a population mean. You've got right here mu equals sigma x over a capital N. And mu is the representation for the population mean. Sigma, anything that comes after sigma, means sum that up. Okay, so it's saying sum up all of the observations. So x is the number of observations in a particular population, and then divide it by the total number of values in that population. So if you have 360 cars, you're going to sum up all 360 observations, and then you're going to divide it by n. And in this situation, that 360 would have to be the entire population. Like, for instance, if you're looking at all of the cars that were sold at an auto dealership for the entire year or for an entire month, that would be a population. But if you're looking at just a sample or a portion of those cars, then that would be a sample of the population. So yeah. So a measurable characteristic of a population is a parameter. Okay, so you're looking at the population mean. That's a parameter of the population. And when I say population mean, you're looking at a population mean of a statistic, or sorry, of a population mean of a characteristic. So here's an example of a population mean. There's a total of 42 exits on I-75 through the state of Kentucky. Below is listed the distances between those exits in miles. So the question is why is this a population? Why is this a population? Is this all of the exits on I-75 through the state of Kentucky, or is this just part or a sample of the exits? And the answer is it's all of the exits on I-75 through the state of Kentucky. So this is the population of exits on I-75 through the state of Kentucky. And the next question is what is the mean number of miles between exits? Because we want to know what is the average, or what is the mean distance. So we're going to look at the population mean. Mu equals sigma x over n, so it's sum up all of the distances between exits and then divided by the total number of observations. So the sum of all the exits, or all the distances between exits, is 192. And then you divide that by 42, which is the number of observations, which gives you the average distance between exits is 4.57 miles. And that's a population characteristic, okay, or a parameter, if you will. So a measurable characteristic of a sample is a statistic, okay? So if I ask for the parameter of a population, the mean of a population is a parameter. So the mean of those distances is a parameter. But if I'm looking at a sample, then that would be called a statistic. In the example of a sample mean, instead of utilizing mu for the symbol, you're utilizing what is referred to as x bar. X bar equals sigma lowercase x over lowercase n, and n represents the number of values in the sample, and x represents the value of the observation in that sample. And once again, sigma is a capital Greek letter, and sigma x is the sum of the x values in that sample. So, moving on, let's look at an example. Verizon is studying a number of minutes used by a client on a particular cell phone rate plan. A random sample of 12 clients shows the following number of minutes used last month. So you look at all of these and you want to know what is the average number of minutes, or what is the mean of the minutes utilized by individuals in this population. And so you do the sum of the values. So you sum up all the values, which is 1,170, and you divide it by the total number of observations, which is 12, which gives you an average or a mean of 97.5. Now, before I said, how many minutes, what is the average number of minutes in the population, I'm well aware that we're only looking at a sample, but often when you look at samples, what you're attempting to do is actually utilize that sample and generalize it to the population. It is very expensive and very difficult to obtain all of the information for an entire population. And so often you'll pull a sample out and try to generalize the statistic from the sample to the population and say this statistic is representative with error, and we'll get into that a little bit later, to the population. So that was the arithmetic mean. Now we're looking at the median. So the problem with an arithmetic mean is it is... Oh, I skipped over a slide, and that's why. Okay. Intervals, or these are properties of arithmetic means. Intervals or ratio scale of measurement is required. You can't do this with ordinal, and you can't do this with nominal. Okay? All data values are used in the calculation, so you have to include everything, every single observation in the sample. Okay? It's unique. It's not going to be the same as another population or another sample, and the sum of the deviations from the mean equals 0, which we haven't gotten into deviations yet, but we'll get into that soon. But the biggest issue with calculating a mean is that it's affected by extreme values. So in the next slide, if we were to calculate the mean, we're going to use an extreme value, and we're going to demonstrate why it would be appropriate to utilize a median instead of a mean when you're encountering extreme values. Okay, so the median is the midpoint of the values after they've been ordered from the minimum to the maximum. Okay, so the minimum is the lowest value and the max is the highest value. And you look at this data set and you see, you have 275,000 for one, but all of the rest of them are within $20,000 of each other. And what we're looking at here is the price of condos in a particular city. Okay, and so one condo in the sample is $275,000. If you were to do the mean, it would drastically skew or alter the measure of central tendency, and the mean of this would actually be $110,000, which doesn't really represent this sample very well. So in this situation, because of the extreme value, it might actually be better to utilize the median. And the median is you order it from minimum to maximum, and you take the value that is in the center. In this case, it's 70,000 is in the center of the sample. Okay, so characteristics of the median. The median is the value in the middle of the set of the ordered data, like I just said. And at least the ordinal scale of measurement is required. So if you wanted to, you could do this with ranked data. Like I said, you can't do mean with ranked data, but if you have ranked data and you want to find, who's in the middle of this pack of, individuals who were in a race, and this person was in the middle of the pack, you can do that with mean data, with median, or you can do that with ordinal data. And it's not influenced by extreme values, which is a really great strength of it. 50% of the observations are larger than the median, and 50% are lower. And it is unique to that set of data. So let's find the median. Okay. So first we need to sort the observations and calculate, in this particular situation, we're looking at an even numbered set. There's a total of 10 adults. So what happens when there isn't someone smack dab in the center? Okay, so you order these in order from minimum to maximum. That's the first thing that you always do when looking at the median. Okay, so 1, 3, 3, 5, 5, 7, 9, 9, 10, and 17. So you look at the fifth one, which is 5, and then you have 7. And what do you do when you have that? And the answer is you take the the fifth and sixth observation and you average the two. Okay, so the median is 6. The mode is a different measure of central tendency, which is unlike either of the other two, and all that we're looking at in this one is which of the observations occurs the most often. Okay, so the mode is or with the greatest amount of frequency, and you can utilize nominal data for this. So which is a qualitative, the lowest level of qualitative data, and all that you want to know is which one occurs the most often. Okay, so a set of data can have more than one mode. In that situation, it would be referred to as bimodal. Okay, so let's go back here. So you have, this would actually be trimodal. So you would have 2 3s, 2 5s, and 2 9s. And so you have a trimodal set of data. Or going back, let's see here. Here, do we have a mode? We don't have a mode. Let's see, 90, 91, 70. No mode at all in this set of data. And so often modes work really well with larger sets of data as compared to having a smaller set of data where you only have 10 or 11 observations. You might not even have a mode. Let's see here. So this is something that's really important that we're going to get into a little bit later. We're looking at relative positions of the mean, mode, and median. Okay, so if the mean, median, and mode are all identical, then you have a relatively normal distribution. If the median is if the mean is greater than the median, then you have a positive distribution. And if the mean is less than, or positively skewed distribution, if the mean is less than the median, then you have a negatively skewed distribution. And we're going to get into that a little bit later. The mode, like I said, is which one occurs the most. And it's not used nearly as often, but there's definitely situations when you would want to know, which one of these occurs the most often. Like, for instance, if you're at an academic fair, which booth gets visited the most often? It really works well with nominal data as compared to ratio or interval. But if you have ratio or interval, or even ordinal, the mean and the median are really what's going to be utilized the most often. Okay, so we're going to get into the weighted mean now, how to calculate the weighted mean. So the weighted mean is something that you can do when you do have, multiple observations of a single or of multiple observations. Okay, so for instance, Carter Construction Company pays its hourly employees $16, $15, $19, or $25 per hour. There's 26 hourly employees. 14 are paid at 16.5. 10 are paid at 19, and 2 are paid at $25. So what is the mean hourly rate paid for the 26 employees? If you wanted to, you could add up 16.5 14 times, $19 10 times, and $25 2 times. But instead of doing that, you can just multiply 14 by 16.5 plus 10 times 19 plus 2 times 25, and then you divide that by the sum of the observations. So in this case, in 1 hour, $471 is the sum of the hourly rates, and you divide that by the total number of employees, or the total number of observations, which is 26, which gives you the weighted mean of 18.115. In all honesty, this isn't any different than the arithmetic mean. It's just combining all of the observations of a particular number and multiplying it, and it just kind of makes it a little simpler. So the geometric mean, however, is completely different than the arithmetic mean. The geometric mean is the nth root of the product of n positive values. And this is really looking at like the rate of increase over time, or the average percentage of change. Okay, so to really look at this, we're going to do this in Excel. Okay, so the formula is, like I said, the nth root of the multiplication of multiple observations. So say, for instance, you're working at a company and they promised you that you were going to have a 10% raise every single year. And you wanted to see whether or not they actually gave you, on average, a 10% raise every year. So the first year, they gave you that 10% raise. And so you signify that as 1.1. So you have your salary plus 10%. But the next year, they had some issues with income, and they actually had to dock your pay by 30%. Okay, so then you signify that by 0.7, but notice it's still positive. So the next year, they had a really great year, and they wanted to reward you for sticking it out, so they gave you a 30% raise. And the year after that, they gave you a 10% raise and a 10% raise. And you want to know, did they really, on average, give you a 10% raise during your time there? And so the way that you do this is you do equals times multiplied by multiplied by multiplied by equals. Okay, so that's 1.21. Let me just make sure that I did this correct. Yep, there's 5 there. Okay, and you want to take the geometric mean of that, and the way that you do this is you equals raised to the fifth. Oh, sorry. Raised to the 0.2. And in all actuality, the average raise that you got over the period of time that you were there was a 3.9% raise. So that hit of 70%, or that hit of a decrease in pay of 30%, really messed with your raises over the course of your time there. At this point in time, you go to the boss and you say, hey, over the course of time, I've only gotten an average of a 3.9% raise. I want a large, let's see here. So you notice that I did this particular number raised to 0.2, which is the fifth root of this number. So the way that you do this is you do equals this number raised to 0.1 multiplied by 10 divided by how many ever numbers you are, how many number of observations you are counting. So we're going to look at, for this upcoming year, you want another raise. Okay, so what raise would you need in order to be able to get to that 10%? So maybe a 35% raise. Let's take a look at 35% raise. That still wouldn't even get you there. So let's look at a 45% raise. Almost. You might need a 50% raise. Yep, you need about a 50% raise in order to get back on track with what they promised you when you first started, which is really nice. So go into your boss and tell them, hey, I need a 50% raise, and see what happens. Okay, so that is the geometric mean. The other way that you could do this is to take the nth root of the value at an end period as compared to the value at a start period. Okay, so if you're looking at, you want to look at the rate of increase over time, and you want to find out the monthly increase over time, you look at the value at the end of the period. So say, for instance, it's 145. And then the value at the start of the period was 132. And then you can do equals divided by 1.098. And then you can take the 12th root of this. And the way that you do that, once again, is equals raised to the 0.1 multiplied by 10 divided by 12. Okay, and the rate of increase, then you subtract 1 from this, so equals minus 1, and that gives you you have a 0.78, or you can do, let's see here, percent, a 0.79% increase per month, which isn't a whole lot. So that's the rate of increase over a 12-month period. So you look at the start versus the end. And that's pretty much all that we've got for the mean, mode, and median.